Hello everybody, glad to see you. Today we're going to talk about total runout. At top right, we can see this symbol. This symbol is going to represent total runout. In first example, we are going to implement total runout. We can see here it's going to refer to this surface. Tz is 0.03 back to A. A is axis of this cylinder. It means we are going to have two coaxial cylinders with a distance of 0.03. And that profile should be in that interval while we are going to rotate the component and dial indicator is moving left and right on this surface. We are going to control form, orientation, and location. It is 3D version of run out. In run out, we are going to control off center and form of the cross section. But here we are going to control the location as well. We are going to cover the concentricity because in concentricity we are going to find the median points respect to that axis, and we are going to have a 3D cylinder and all midpoints should be in that interval. By using total runout, we are going to control concentricity as well. Somehow we are going to control orientation the same as perpendicularity and parallelism. In this slide, we can see circularity. We are going to have two coaxial circular. We are going to have cylindricity. We are going to have two coaxial cylinders. And concentricity, we are going to see the mass distribution with respect to that axis. And circular runout, we are going to have 2D version of total runout. We are going to control the form and orientation and somehow off center of each circular in each cross section. We are going to cover all of them by using total runout. Here at top, this total runout is implemented for this surface. Tz is 0.5 back to AB axis. We are going to have two coaxial cylinders, and that profile should be in that Tz when we are going to rotate the component, and dial gauge is going to move on this surface, left and right. Here, we are going to implement total runout for this flat surface. Tz is 0.5 back to AB. What does it mean? It means we are going to have two parallel surfaces perpendicular to AB axis with a distance of 0.5, and this feature should be in mentioned Tz. Somehow we are going to control the perpendicularity or parallelism in this situation whenever we are going to implement it for flat surface. Here we can see at the top we are going to have this total runout Tz 0.1 back to A. We are going to have two coaxial cylinders with the Tz 0.1, and that profile should be in that interval whenever we are going to rotate the component around A, and the indicator is going to move in this surface. And also at the bottom, we are going to have, we can see at the bottom left, we are going to have this total runout Tz is T back to BC axis. We are going to have two coaxial cylinders that are highlighted by blue dot points, and that profile should be in that Tz whenever we are going to rotate the component, and dial indicator is going to move on this surface. Here we are going to have another example at bottom right. We implement total runout for this flat surface. Tz is T, and back to BC axis. We are going to have two parallel surfaces perpendicular to BC axis, and we are going to control runout for this surface. Here in last slide, I would like to compare perpendicularity with total runout. Perpendicularity, as we can see at top left, we are implementing for this surface, and TZ is 0.08 back to A. It means we are going to have two parallel surfaces perpendicular to A, and that surface should be in that interval. We are going to have the same meaning whenever we are going to use total run out, because here we are going to rotate around axis A, and whenever it's going to rotate around that, the dial indicator is going to move up and down, and then that profile should be in dimension TZ. Somehow we are going to control perpendicularity by using total run out. For now, I would like to close this session. In coming session, again, I'm going to talk about total run out. Thank you for today. I hope you enjoy it. See you next time.